Yeah.
You can like get factors from 55, right? Without like putting them all under the same thing. That's what I did. I did like radical 5 times radical 5 times radical 11.
Yeah. Yep. So Stephen asked, can you do the ladies? We'll wait for you. I'm good. You guys good? All right. Stephen asked if you can just kind of write the factors down where you could come up with 275 is 5 times radical 11. Then he realized that it's the square root would just be 5. That works out well too. All right. Our second one. What's wrong with the second one? What's wrong with it?
Question on the previous one.
Okay,
I'll
yeah.
answer the next one. But so is it just a coincidence that it's 5? Like the
Yes.
answer is
Yes.
Okay.
Yes.
Okay. And then I'll do the second one. Well, the problem is that we have a fraction under the radical.
So what do I need to do first?
You need to isn't it convert it?
Yeah.
So it'll be like.
I'll just say we're breaking it apart, right?
No, do that.
Yeah. We're breaking it apart or
Is that the
converting
same
it.
thing, though?
Yeah. Yeah, both those things are the exact same.
But you can have a radical in the denominator.
Yep, but we're not allowed to have a radical in the denominator. So what do I need to do to get rid of the radical in the denominator? Yeah.
You can either multiply the top and bottom by square root of 42 or just like break them up into like the littler.
Oh, simplify, and then yeah. So two ways. You could simplify everything along the way, and then at the very end, you're kind of multiplying by a small radical. What did I do in my notes? I think I did.
7, 2, and 7.
Oh, you know what? I did this really hard way. Let's do this the easier way. Yeah, let's just divide it first of all. Let's simplify this. What could 14 over 42 be simplified to? I don't know why I did that. Yeah, Amber.
2 to 6. Oh, that's so easy.
Well, I did that.
Okay.
Yeah, Steven.
Wait, can't it go to 1/3 though?
Yeah.
Oh.
And now we can break it apart. It probably makes it a little easier because I'd have square root of 1 over square root of 3. First of all, what's square root of 1?
Isn't it just 1?
It's just 1.
Just like I.
It's not I. It's not an imaginary number. It is just 1. So what we really have is 1 over square root of 3. Now all I have to do is multiply the top and bottom by square root of 3. Yeah, it looks like a lot of steps, but on your notes you probably wouldn't have put this much work into it. Square root of 3 over 3. Okay, pasa.
Wait, so when we're like doing ones with fractions, like I just did square root of 2 times square root of 7 over square root of 7 times square root of 3 times square root of 2, and like 2's and 7's canceled out, so it's just 1 over square root of 3, and like I simplified it with does that make any sense? I don't know, it was working.
I think so. I think what you're talking about is like so an alternate way you could have done this is you did like square root of 7 times square root of 2 on top.
Yeah, and then 7, 3, and 2 on the bottom.
7, 3, and 2 on bottom, and she just noticed that these canceled out, and you end up with 1 over. Yep, that works as well. Yep. There's multiple ways to do these. Usually when you get better at them, you just kind of know which factors go into it, and simplifying becomes a little easier. Plus, once we get out of this unit, we have a lot less of the complicated ones. Usually it's really quick, easy ones. It's like, I'm trying to think of an easy one, maybe like 20, square root of 20, where you know like 4 goes into it. That's more realistic. We kind of throw the really hard stuff at you to practice it, and then usually we ease off. We don't give you crazy ones. And when we get to upper level math, square root of 14 over 42 probably is an okay answer. All right, yeah.
Will all the shoot, what do you call it?
Radicals?
Or like the equation that gives you to begin with, like they will all I don't know. Let's just say it's like radical 6 times I don't know, like 70. It would look like the one on the bottom, right? It would all like the same format where it's the 5 radical whatever. You know what I mean?
No. I'm not sure what you mean.
Okay, I'll ask you. Kind of difficult.
Okay.
Explain myself.
Yeah, just find like an
Yeah.
example, and then I'll answer it. All right, I'll answer questions from the homework after. Make sure you knew how to do that homework. Like I said, hey, this is mostly review. That's what that whole thing was, is reviewing how to do radicals. So if you're struggling with it, make sure you come see me. I'm here before, after school, lunches, breaks, or anything like that. Come ask for help. The last thing you want to do is get to this test and get points off every single problem because you just didn't know how to simplify the radical. Even though you knew the hard stuff, you just didn't know how to simplify the radical. So on that, is there any questions about either one of these two, how I solved it? Okay, and each person kind of does their own way. Stephen did his own way, which worked. Hannah did her own way, which worked. All right, these are all possibilities. Let's pick the methods that work. Okay, today we're going to talk about the Pythagorean theorem. The Pythagorean theorem in a right triangle. I boxed that in because it's very important. The only time you can use this is in a right triangle. Has to be in a right triangle. We don't use the Pythagorean theorem unless it's a right triangle. So the square of the hypotenuse is equal to the sum of the squares of the legs. Just remember, your hypotenuse is always going to be that long side across from the 90 degrees. That is always your hypotenuse. So your hypotenuse is the one that's across from the 90 degrees. It is always your longest side. So this will always be your longest side. So if I said you had triangle 3, 4, 5, and it's a right triangle, you know the 5 is your hypotenuse. I don't have to tell you it's the hypotenuse. You just have to know the longest side is your hypotenuse. Get that in your head, because there will be times where I say we have a right triangle that's 4, 7, 20. That doesn't work. But if I did, you'd say, okay, 20 must be my hypotenuse because it's the longest side. I'm going to say that over and over and over because today we're not going to do that. But in the future, I can just throw that at you, and you have to know it's the longest side. Important stuff. All right. So what this statement says is basically that a squared plus b squared equals c squared. Side a squared plus side b squared equals our hypotenuse squared. And that will work for any right triangle. Now we're going to do a super fancy proof with tons of theorems and postulates and sound like fun? No? We're going to do kind of these are more arithmetic proofs. We're not going to put any theorems or stuff down. We're just going to put facts down, set stuff equal to each other, and solve an equation to show that it's true. So we have two rectangles, almost squares. Would we agree that the area is the same in both of these? If all these lengths are the same? Yes, we would. All right, so what I want to do in this first one, is I want to get a line tool. I mean, not a line tool. I'm going to freehand this. I'm going to connect these red dots. Yours probably aren't red because yours aren't in color. And I'm going to put the area of each thing. Remember, area is length times width. So this one is a squared. This one would be a times b. The lower left-hand one would also be a times b. And finally, the bottom right one would be b squared.
It doesn't matter if you say like BA instead.
No. And you'll see why. Just make sure they're both BA. Try to keep them both the same because we actually have, because these two are the same. So I'm going to end up saying there's two ABs. So there's two ways to write this area. Area either equals A plus B squared, because that would be A plus B times A plus B. The other way you can write the area is just add all of these sums together, which you could also FOIL that and get the same answer. So area can also be written as, well, we have an A squared plus the two ABs plus that B squared. And in fact, that's why like FOILing and stuff works. is you can break it down geometrically, and you're foiling where you do your first outside, inside, last, when you're doing a binomial times binomial. This is why it works. It works geometrically, so it works in arithmetic. Well, that's what the area equals. Now, for the next one, I'm going to connect these dots just a little bit different. I'm going to connect them and make some triangles. What was that? Yes. Yeah. They absolutely are. And what I'm going to do is I'm going to label these black lines. I'm going to call them C. Now I'm going to get the area of this. But I haven't pointed out a great point that all 4 of these triangles have the exact same area. What's the area of a triangle? Does anyone remember? Amber?
180. Oh wait, no, that's not.
It's 180.
Never mind.
Okay. Actually, half the base times the height. So area equals 1/2 the base times the height. So in this case, each triangle is going to be 1/2. I want to make sure it works out. I don't remember if I want to put my A or my B first. So I'm going to put my A first. 1/2 A times B. That's the height of one triangle. So our total area is going to equal, well, how many of those triangles do we have? Yeah,
4.
we have 4 of those triangles. So to get the area of each of those bits, like here, I have 1, 2, 3, 4. So our total area is going to be 4 times the area of one triangle. So that's 4 times 1/2 times AB. Yeah, Stephen.
Can't you simplify it to 2AB?
Yeah, we're going to. But is that the area of the total thing yet? That's just the triangles. What would be the area of this? If that's C, they'd all be C because they'll all be the same length. Well, that's just going to be plus C squared, because the area inside here is C squared. So like Stephen said, let's distribute this 4 to come up with 2AB plus C squared. Now these are the exact same size, so the areas must equal. So even though this is written this way, and this is written this way, they both must be equal to each other because they're both the area of these 2 given squares. So what we're going to do down here is we're actually going to set them equal to each other. So we're going to say the areas are equal to each other, so A squared plus 2AB plus B squared is going to equal 2AB plus C squared. Well, the only thing I could do to simplify this would be to subtract 2AB from both sides, or 2BA if you wrote BA instead of AB. This would cancel, this would be canceled, and in fact you're left with A squared plus B squared equals C squared. It's arithmetic proof. I didn't actually say I'm allowed to subtract things on both sides. I didn't put the subtraction property of equality or anything. But this proves that A squared plus B squared, so when we have an A squared plus a B squared, is going to equal that diagonal that's right between them that we named C squared. Probably one of the most interesting proof. What was that?
I'm just shocked right now.
Where did I lose you?
So, no, I'm just,
Oh.
so B squared equals C squared.
A squared plus B squared equals C squared. Yep, that's what we're left with. You had that right?
Yeah.
Yeah, you have A squared plus B squared equals C squared. Yeah.
I was just looking at it.
Yep. Just smile and nod. No, it works out. It works out. It proves that we can use the. you need to see this stuff because this is why it's true. Someone had to prove this back in the day to show that it works for every single triangle. Because the problem with math is if it works for a couple things, that's not a proof. I can't just be like, well, it worked these 3 times. You have to come up with some kind of proof that solidifies that it'll work for every single triangle after it. So that's why proofs are important. All right, continuing on. All right, we're going to find x by using the Pythagorean theorem or a Pythagorean triple. We're not going to use the Pythagorean triples. We'll talk about that later on. I shouldn't even have put that in there because we aren't going to do that. We're just going to use x by doing the Pythagorean theorem. So just remember, your hypotenuse is the one across from the right angle. So you have to set this stuff up right. Well, 3 is a leg, x is an egg. So the way we're x is a leg. So we're going to have 3 squared plus x squared equals 5 squared. The biggest mistake people are going to put on the test is they're going to mix that up. They'll put 5 squared on the wrong side. Hypotenuse always goes on one side by itself. All right, 3 squared is 9er plus x squared equals 25. Subtract 9 from both sides. And you're going to have x squared equals 16. Now, when I take the square root of both sides, technically, we're going to get out x equals plus or minus 4. But like I said, we're in geometry. We can't have negative lengths. You can't have negative lengths, so we aren't going to do plus or minus 4. It is just going to be plus 4 or just 4. It's good to remember when you get to the next math class that you're getting to, Algebra 2, it will be back to plus and minus, but for our means, we can't have a negative 4, so it's just going to be plus 4. All right, our next one, let's recognize the hypotenuse. It's x squared, so that one has to be all by itself on one side. So we are going to have 4 squared plus 6 squared equals x squared. Well, 4 squared is 16. Plus 6 squared is 36 equals x squared. Yeah.
Wait, can't we just automatically just square root everything?
No.
Why? Like why though, honestly?
Honestly, let's do an example that you would do that. Let's do 2 squared plus 4 squared. Well, that's 16 plus 4 would equal, let's just say 20. Now you're saying it's okay just to square the entire side and get rid of the square roots?
Isn't it x squared? No, wait, can you go back to the slide?
Sure. So normally it's x squared.
Yeah, but why can't we just...
I'm showing you here why we can't. So we can't even do it with... So do you agree that 2 squared plus 4 squared equals 20?
Possibly. Yes.
Yes, so that's true. So you're telling me if I take the square root all the way across that it'll still remain congruent?
Well, what I did was I just did that to get rid of that. So I got x equals 4 plus 6. That's what I did.
Okay, let's go down your... So you have x equals 4 plus 6, right?
Yeah.
Let's see if we come up with the same answer. So I'm doing 16 plus 36, which would be 52, equals x squared. I take the square root of both sides. I'm going to have x equals the square root of 52. Is there a perfect square that goes into 52 at all?
No. Yes. No.
Wait.
No. So the answer is x equals square root of 52. Did you get square root of 52?
1 second. No, what I did, I square rooted 4 squared plus 6 squared equals x squared to get just 4 plus 6 equals x, and then which equals 10. So the 10 equals x.
So your way doesn't work. You can't take the square root of both sides. You have to do addition first. You can't take a square root. You have to add under the square root first.
Okay. But is 52 the actual answer?
No, it is not done yet.
Oh.
There is a perfect square that goes into it. Yeah, Sabrina.
4.
4 goes into it. 4 does go into it evenly. How many times does 4 go into it? 13 times. Perfect. So this one actually reduces down to 2 square root of 13. Make sure you do the little checks. 4, 9, 16. Just do a quick check. You have calculators in your hands, right? Just check it. Just check it. So, especially when it's like 52, it looks like 4 goes into it. It's a nice even thing. I always try 4. At the very least, I always try 4 to see if that goes into it. All right. Ooh, do I not? Did I? Oh, I did not erase it. All right, next one. Our hypotenuse is 12, so we are going to have 4 square root of 6 squared plus x squared equals 12 squared. Well, 4 times square root of 6, we can think of that as being 4 squared times square root of 6 squared plus x squared equals 144. Well, 4 squared is, yeah.
Or we just left with 2x, or sorry, 4 squared times 6, right? Because it doesn't.
Yep. So we'll have 16 times 6, right? Because 4 squared is 16. Yes, absolutely we would. Which should be x squared equals 144. Akshay.
Wait, for all our answers, do we just express them in like decimals? Do we have to use like the radical?
Have to use the radical. Have to use simplified radicals. Otherwise, the section would be really easy for simplifying radicals because you go, I'll just get rid of it by putting a decimal. No, we have to leave everyone as a radical. All right, so we are now going to have 96 plus x squared equals 144. I'm going to subtract 96 from both sides, and I wind up with x squared. I have those right? 96, yeah, that's right, equals 48. I just don't want to get any further and find out that 6 times 16 isn't 96 when I did it in my head. But that makes sense, 60 plus 36. All right, now I'm going to take the square root of both sides. It is not a perfect square root, so we have x equals square root of 48. But is there any perfect squares that go into 48, Sabrina?
4, radical 4, radical 4, radical 3, and that would be 4 radical 3.
4 radical 3?
Yeah.
Yeah. So Sabrina broke it down into radical 4 times radical 4 times radical 3, which he said is going to be 4 square root of 3. Another way you could have done it is you could have done, well, square root of 16 goes into it 3 times. Either way, perfectly acceptable, and we come up with 4 square root of 3 is that one. I'm just going to let you do the next one and then start the homework. So you're going to do the next one and start the homework if you haven't already. You should come up with x equals 15 for the last one. X equals 15 for the last one. Yeah, Sabrina.
I'm a little bit confused on like setting up the problem.
Okay. So we're going to do it the exact same way.
10 over 3.
So,
10 radical 3.
yeah, you got it, except we're not going to put
Should
x
you do
squared.
D
We're going
yet?
to actually square the whole thing.
On the,
So you see mine, I have x squared plus x squared
I got x.
equals the
How'd
whole
you do that?
quantity squared.
I got x squared.
And that would be
How do you get x squared equals x squared?
Yeah, so, yep, so we don't
Oh, I
want
found a
that.
square. I'm just a dingus.
Exactly.
oh, I put it in parentheses like as in square.
They cross out the
Yeah.
x's.
But give it an x
I
squared.
did the x squared minus x equals, yeah. I was
That's-
making my life
that's
hard.
square.
Yeah, there's no square there. Yep. There we go.
And then that would be
16.
Not quite. Hey, quick heads up. You should have